Hi. So, when was the last time you sat down with your grandmother and had a conversation about p-values or precision and recall, or chatted with your uncle about a ROC curve? We don't do that. We don't really sit down and talk about data science concepts with sort of the general public or people in our day-to-day lives very often because those concepts are really or can be really hard to understand. On the other hand, there's a technical instrument, a data instrument that many of us, that almost everybody in this country or in this world kind of knows how to read, and that's a map. And my name is Seth Spielman, and I'm here to talk to you today about data science done on maps. And data science on maps is pretty cool and pretty interesting, in part because it's so intuitive. They're such intuitive instruments, but also in part because there are a lot of really meaningful problems that happen in physical space, and being able to engage with those problems creates, I think, a powerful set of skills. So with that, I'm going to share my screen and talk a bit about data science on a map. So here, this is a map, or sort of a map. This is an image taken from a satellite. And pictures like this are not that miraculous now, but not so long ago, they were pretty game changing. And so this particular image is a false color satellite image showing the kind of Arizona region, and vegetated areas it's a false color image. So vegetation shows up as red instead of green. And right now, images like this are increasingly available. There's been a boom in the kinds of satellites that are available to the public. And satellite information like this is available for much of the world, and is sort of transforming or creating great opportunities for spatial data scientists. The other thing that is sort of changing the world are maps like this. And I'm kind of right, my head is right in the middle of it. Sorry, Australia. This is a map which was created in a very different way. In a lot of ways, it looks the same. But this map is from a company called Strava that, people record their location while they're jogging or riding a bike or something like that. And so this is a map of people doing physical activity. And unlike the map from the satellite, in which a single sensor was circulating the Earth and capturing images, in this case, we have millions of distributed sensors. And each of those millions of distributed sensors is a phone in somebody's pocket or a watch on their wrist that is recording their latitude and longitude. And then all of that information is being assembled together into a map of the world. So it similarly is a new kind of map, a really interesting kind of map, but one that is collected by distributed sensors rather than sort of an eye in the sky. And all of this data that's now available to us, creates all sorts of interesting ethical challenges. So, the data from your phone, the large image on the left is a picture from a New York Times article which talks about the ubiquity of sort of location tracking, that data about tens or hundreds of millions of people around the world are available for sale. And from that information, you can very easily figure out an individual's home and work location, and that can often uniquely identify an individual. The two articles on the right, one talks about that Strava heat map that I just showed you. The other talks about some of the challenges around location privacy in the sort of pandemic surveillance apps. Key point here is that these data create these transformative opportunities, but they also create a whole suite of challenges, ethical challenges for us as current or aspiring data scientists. I think it's important to realize, though, that, spatial data or data on a map is not always the same as regular data. That aside from the kind of unique ethical challenges that locational data can create, there are also just some things to be aware of with spatial data. So here we're looking at the exact same data set displayed two different ways. So the data set on the right, which looks like kind of static from an old analog television or something, contains the exact same data as the image on the left. So same data. However, we can see that the actual sort of the spatial arrangement of the data can really sort of change what the information means, right? On the one hand, if you were to look at an image like this, you wouldn't really ascribe much meaning to it. But here, one could imagine that there was some sort of pattern here. Maybe this is a map of elevation and the white areas are high and the dark areas are low, and this is a mountain and this is a valley, or maybe it's a map of temperature or something else, right? Key thing is that the arrangement of data points, of values in space can really sort of change the meaning of the data that we're looking at. And that's part of the power of maps, is maps give us a way to see that. So I think the spatial perspective is more than just a visual one. I think it enriches applied data science pretty broadly. And so one of the things that's kind of interesting about spatial data science, or thinking spatially in the practice of data science, is that proximity can imply dependence. And so let's hold that idea in our head for a second, that proximity can imply dependence. And there's another idea here that I want to talk about, which is that proximity can imply similarity. Proximity, sort of the co-location of events in space, can also tell us a bunch of stuff. So where events happen, where things happen on a map or don't happen on a map, can also tell us something. So let's think about proximity implying dependence first. So let's imagine that we have three points in space, and we've observed measurements for two of them, but not the third one. So here we have a 10. We've measured 10 whatevers. Let's not worry about what the thing is, but we've measured the number 10. And down here, we've measured the number 0. And the question we want to answer is what's happening right here at the question mark. So if we were thinking about, say, maybe this was a map of temperature, right? If it were a map of temperature, it would totally make sense that if we're measuring 10 degrees over here and 0 degrees over here, the point that's somewhere in the middle would be somewhere between 0 and 10, that there's probably some sort of temperature gradient between these two kinds of things, because that's how temperature works, right? Like, it's rare, it happens, but it's generally relatively rare for you to walk some distance and for there to be dramatic changes in temperature, right? The temperature changes sort of happen as a function of distance from a point. So as we move further and further away from this 10, we would expect the temperature to get lower and lower. So in that case, we're talking about proximity implying dependence, where the values in these two locations or these pairs of locations are probably dependent on each other in some way. We're also talking about proximity implying similarity, that 2 points that are near each other are probably kind of similar to each other. However, let's imagine we're mapping something else and not temperature. Let's imagine we're mapping gunshots, right? And so here, this is the number of gunshots that have occurred in the past week, and this is some sort of urban neighborhood. And there's no reason to suspect that just because there were 10 gunshots at one particular point in space and 0 gunshots at another particular point in space, that we would expect the same kind of spatial gradient around, say, gun violence as we might expect around temperature. And this is because we live in a world where location is often correlated with a lot of other things, right? So location is often correlated with wealth, with culture, with language. So interpreting spatial data can require a lot of nuance. And it's really interesting to think about the data that we have, and when we put it on a map, and kind of figuring out what we can learn from that or not. So the act of doing spatial data science requires not just looking at the data, but also thinking about the data generating process from a social, cultural perspective, or if it's data describing a physical process, understanding the sort of physics of that process and how that manifests in space. So for example, if we were looking at this map, one could sort of make the very false assumption that, that, you know, in the Democratic Republic of the Congo, nobody runs, which is of course not true. It just happens to be the case that this particular app, which is probably used by more affluent people who run for recreational purposes, that you know, the fact that this part of the map is dark, has an absence of activity, doesn't mean that there aren't people here, doesn't mean that there aren't people running here. It simply means that there's a very different sort of cultural and economic situation, that there are deep cultural and economic differences between, say, the Congo and France or California. So what does it mean to do geographic data science? What do geographic data scientists kind of know and do? So geographic data scientists know there's a couple of things that kind of, I think, distinguish them from sort of vanilla data scientists. And these are actually fun things to learn and fun things to do. The first one is cartography, knowing how to make a map and knowing how to visualize data on a map. Maps are really interesting because people have been making scatter plots, I don't know, 150, 200 years maybe. But people have been making maps for thousands and thousands of years. And there's deep wisdom, as well as sort of a deep kind of human intuition around maps. There's also been centuries of sort of refinements of the craft of map making. And it's really interesting, I think, to understand that. And I think that makes you better at visualizing all forms of data. So geographic data scientists know something about cartography. Spatial data comes in some funny formats. Spatial data scientists know how to handle those funny formats and to use the software libraries that sort of handle those things well. And those exist in sort of every major programming language that a data scientist would use, whether that's Python, R, Scala, whatever it is. There are ways to handle spatial data, but they're different. Spatial data scientists know how to think critically about the social and technical aspects of data generating processes. So that's what I was talking about before, understanding what the absence of data in a place might mean. Does it mean that nothing happened, that nothing was measured, that it's a different kind of regime? They understand GPS and remote sensing. So the basic technologies, remote sensing is satellite sensing from satellites. The basic technologies that generate a lot of the data that are used by spatial data scientists. Spatial data scientists understand a special suite of techniques called spatial statistics. These are techniques for reasoning on graphs, for detecting hotspots, for dealing with interpolation problems. Those are problems sort of estimating information in unobserved locations. Spatial data scientists often know quite a bit about spatial optimization techniques. So these are things like routing, regionalization, location and covering problems, and things like that. So it's a kind of subset of geographic data science, of regular vanilla data science. So just quickly, I thought I'll just talk briefly through a case study of some of my own work that sort of highlights some of the value of geographic data science. So this is work that was published in an academic journal called the Proceedings of the National Academy of Science, PNAS. And this is work looking at the vulnerability of communities in the kind of northwestern section of the United States to tsunamis. And so what we did is we looked at a bunch of different communities that are vulnerable to tsunamis, and we did a clustering analysis to create sort of different kinds of communities, and those are the colors on the map. And those clusters were defined not so much by spatial information, but by the demographic and economic information describing those communities. So the kinds of people who lived there and the kinds of activities that occurred there. We then took that clustering information, which told us about the sort of fundamental nature of communities, and looked at what that might mean for emergency responders, people who have to intervene in the case, in the sort of, if a tsunami were to occur, how would you know sort of how to respond, or how would you know where to target those response resources? And what we found was using that clustering analysis that was not very spatial. We also did an analysis where we looked at how many minutes the residents of those communities would have to evacuate from a location. And because we also knew a bit about the nature of those residents and where they lived. So from that, we were able to estimate not just how long it would take for the average person to evacuate, but how long it would take to evacuate from certain kinds of facilities like nursing homes and dependent care facilities. And so what this analysis shows you is that there are these three different kinds of communities. The prior map shows you exactly where they are. In group 1A, these red and brown colors show you the number of different people with insufficient time to evacuate based on a slow walking speed or a fast walking speed. And so what we see, for example, is that in certain types of places, these group 3 communities, there are large numbers of people who do not have sufficient time to evacuate. In these group 2 communities, we see that there are large numbers of people, but most of them have sufficient time to evacuate. And in these group 1 communities, we see that there are sort of relatively few people in the hazard zone, and the people who are there have sufficient time to evacuate. So by applying a spatial lens, we were able to sort of better target preparedness or response resources around hazard. So that's my brief introduction to data science on a map or geographic data science. If you wanted to kind of learn more, there are a kind of bunch of techniques that are available, and we hope that that helps. Thanks.